Now, the next scientist in line is Ernest Rutherford, right? After John Dalton, then J.J. Thomson. The next scientist you are going to explore is Rutherford. Remember that J.J. Thomson discovered the electrons, right? And he gave the plum pudding model of the atom. And he was like the atoms, the negatively charged and the positively charged particles are uniformly stacked. After J.J. Thomson, we have another scientist called Ernest Rutherford that also tried to explore the atom through an experiment as well. The name for his experiment is the alpha scattering experiment. So alpha particle scattering experiment. We use alpha particles to actually do this particular experiment. So when we say alpha particles, these are positively charged helium atoms, right? So He2 plus, right? So we use that to that we call it. So if you have a helium atom that is in positively charged with two positive charge, that's when you have a helium. We call it alpha particle. So we use alpha particle to do this particular experiment, and this then figure. This is how his experiment look like a setup. So you have a lead block, and then there's a radium atom inside firing a flow of alpha particle. The radium atom, the function of the radium atom is serving as a source of the alpha particle. Right? It's serving as the source of the alpha particle. And we say alpha particle are positively charged radium atoms, right? So it fires that, right, onto a thin gold foil. This is a gold foil, right? He has gold foil. Then he fired a beam of alpha particles onto the gold foil, and then the outcome is that we are seeing most of the gold foil passing through here. Most of them are passing through here. Some of them are undergoing deviation. Some are deviated like this, and some are deviated backward. That's the general view, right? He fires a beam of alpha particle onto through a thin foil, and the outcome is that most of the alpha particle comes out, right, as a glow on the screen, and then others were deflected. They passed through, but then they were deflected on the way, and then some were deflected backwards altogether. They didn't even pass through; they were bounced back, right? So that's the basic view of his experiment. Um, so let's describe that wall. So Rutherford fired beams of alpha particle through a thin roof wall onto a glass vessel where they appear as glues. So if you understand this particular thing I just said here, then describing it shouldn't be a problem at this stage. So now those are the observations. Let's really look at the observation one by one and then draw conclusion out of them. So the observation one is that most of the alpha particle pass through the foil without deflection. So we can see here that most of them are passing through, most of them, the word is most of them are passing through the wall without significant deviation or deflection. And that's the first observation. So that's what we are zooming in more, and we are seeing them passing through, most of them passing through without any deviation, right? So, but if you have that as an observation, what will be the corresponding conclusion? The conclusion that he made is that a large portion of the atom is then made up of empty space. So if most of them are passing through, then mean that nothing is coming on their way, right? So if most of them are passing through, nothing is coming on their way. It means that the entire atom, a large portion of the atom, is made up of empty space. That's why they are passing through, and then they are not undergoing any significant deflection, right? So that's what the first observation is. So most of the alpha particle pass through the gold for and without deviation, and the conclusion from that is that the atom is made up of a large portion of the atom is made up of empty space. That's why most of them are passing through freely without significant deviation. So that's the conclusion for the first one. Another observation is that few of the alpha particles were deflected at small angle. So you see that some were passing through, but you see if you look at this particular one, this one we hit something in the middle and then were deflected at very small angle. It is the same as those that passed through and they didn't bounce back, but they passed through all right, but they were deflected at small angles. So they didn't go straight all right like the rest, but there are few of them just go and bounce to different directions when they hit that. So that's the second observation. So the second observation is basically that few of the alpha particle, the word is few. So remember the first one, the word that we focused on was most of them. So most of them. But this time we are focusing on few of the alpha particle were deflected at small angles, right? So yeah, that this one that hit and then just bounce back, deflect at very small angle. Those are the guys. Now let's talk about the conclusion from that. So if they were deflected at a small angle, then the particles, it means that the particle came near a small centrally placed positively charged particle called the nucleus. Now, pay attention to this one. They came near a small centrally placed. So this something is inside at the center of the atom. That they came near it, right? When they came near it, there is a bit of what? Deflection. What caused that deflection? So we say that the alpha particles are already positively charged. We say the alpha particles are positively charged. So if they are undergoing deflection, it means that whatever they are being deflected from, that particular thing is also positively charged. Because remember, we said like charges repel and like charges attract. So if a positive charge will reflect, meaning that it has made something that's also positive, and the two of them will repel, right? So that deflection was because they met something in the middle, and that middle thing also positively charged. That's why they were deflection away. If the thing was having an opposite charge, then it should have been an attraction. But here it is what? A deflection. So that deflection is as a result of the particle that is centrally placed also being positively charged. So that's what we have here. So he said uh, the particle came near, they came close. When they got close, then they got deflected near a small centrally placed positively charged particle called the nucleus. So that centrally placed particle is called the nucleus. In this place, is represented by the red ball, right? So that's the nucleus in the center. So they came near and they were deflected sideways, a small angle. That's the observation 2. The last observation is that very few. Remember, this one we said few. We say few, but the last one we are saying very few. Very few. Those are the things that you suppose. So we have most, few, and very few. Most, few, and very few. So very few of the alpha particles were deflected backwards, right? Some were deflected backwards, just like this one. It's like how this one was deflected backwards. Most passed through, few were deflected at small angle, but then very few were deflected backwards. What's the explanation to that? The explanation is that the particles they made a head-on collision, meaning as for them, they didn't come near, but they went directly, and on their path, they directly made a head-on collision with the centrally placed nucleus. Right, so they were deflected backwards. That's what happened. So when they were moving through, while others were moving through empty space, some were getting closer to the nucleus, some very few hit the nucleus directly, and they made a head-on collision. They are very few. So this is only very few put through. It means that that particular nucleus probably having a very small size, right? Yeah. So those are the so most of the alpha particle particles are undeflected. That means that a large portion of the atom is made up of empty space. Few of the alpha particles were deflected at small angle. It means that the particle came near a centrally placed positively charged particle called the nucleus, right? And then the last one is the main of the is that very few of the alpha particles were deflected backwards. Very few were deflected backwards. It means that this particle made a head-on collision directly with the nucleus, and so they were deflected backwards directly, not even sideways, but backwards directly. So now, from those observations and conclusion, then Rutherford has a model as well. He also proposed a model from his experiments, right? And from that experiment, the very first one is, he said, so the very first 4 is going to talk about the nucleus, and the remaining 2 is going to talk about the electrons. So keep that in mind. The structure of his model in such a way that the very first 4 that you're going to see, they are going to talk about the nucleus, and the last 2 are going to talk about the electrons. So you are going to be 6 in general. So because Rutherford generally we say that Rutherford discovered the nucleus. Rutherford discovered the nucleus. So the very first 4 are going to talk about the nucleus. So let's see how it goes. So the first one is that the atom contains a solid centrally placed particle called the nucleus. That's the first thing. So the nucleus is at the center of the atom. So the atom of the solid centrally placed particle called the nucleus. That's what he said. The next one is the nucleus contains positively charged protons and neutral particle called neutrons. So basically, the nucleus contains protons and neutrons. And then the neutrons are neutral, and then the protons are positively charged. So when you have a neutron and a positively charged, the total effect is the positive charge, right? So the nucleus is generally positively charged. Neutrons doesn't contribute any charge at all. So the nucleus is positively charged. The second point is just telling us that nucleus is positively charged. The first point was telling us that the atom contains nucleus, which is at the center of it. The next thing is the mass of the entire atom is concentrated in the nucleus. So if you take the entire atom, right, the mass of it, the heaviness of it, the weight is actually in the nucleus. So the nucleus contains the mass of the atom. So if you want to measure the average mass of the atom, you have to go to the nucleus. So that's the same nucleus, right? All the weight is there. Okay. The fourth thing is, so these two came together. The fourth thing is the nucleus occupies a very small volume compared to the entire atom, right? So we say all the masses are inside the nucleus, but then if you talk about volume, if you talk about the volume or the size, it is very small compared to the entire atom. The atom is large, the atom itself is large because it has shells and things, but the nucleus is small at the center, but it's heavy. It's small but heavy. And if you talk about its volume or its size, the size is very small compared to the entire atom. That's what we mean here. So the very first four, I say you're talking about the nucleus. So all these ones are talking about the nucleus because he discovered the nucleus, right? So first, the nucleus, the atom contains nucleus at the center. This nucleus contains protons and neutrons, right, making it positively charged. And then the mass of the atom is concentrated in that nucleus. Then the size of that nucleus is very small compared to the entire atom. That's what you say for the first four. Now let's look at the last two. The last two is I'm talking about electrons. He said negatively charged particles called electrons move around the nucleus in orbits. Like that's what he said, right? We look at the model of the atom already. So he's saying that the electrons are negatively charged and they move around the nucleus in orbits. Simple as that. And then the sixth one is the electrons. The electrons have negligible mass and are spread in a large volume of empty space in the atom. So yeah, so the electrons are, they don't have mass. We look at when we're comparing their mass, they are almost zero. So they don't have mass and they are spread in a large space of empty space in the atom. That's why most of the alpha particles just pass through, right? Because these electrons don't have masses and then they are just spread in a large portion of empty space in the atom. But the nucleus is the one that contains the weight, that contains the positively charged particles, and the electrons are negatively charged particles. So take note that these four, the first four are talking about the nucleus, and then the last two are just basically talking about the electrons, right? So yeah, quick recap. We said we look at this experiment, and then test setup. Then we say first one, most of the alpha particles pass through the four undifracted. Then the next one, this is the conclusion. Then we use few. Then the next one, the last one, we use very few, very few. Keep those in mind, and then try to connect it to their corresponding conclusions. It's up to you to make sure that you understand this particular experiment, and then you use that to make your own conclusions. See you in the next session where we explore another concept in chemistry.